In this video, we will study equivalent circuits. We begin with the definition of equivalent circuits. Two different circuits are equivalent at a pair of terminals if the voltage and current at this pair of terminals is identical for both circuits, no matter what is connected to them. For example, we show two circuits called circuit 1 and circuit 2. Each of these circuits has a pair of terminals A and B coming out of the circuit. The terminals A and B are the pair of terminals that we are referring to in the above definition, at which the two circuits are equivalent. The voltage and current that we are interested in is at this pair of terminals at nodes A and B. For example, the voltage V1 may have the polarity as shown, and we will get the same voltage V1 at the second circuit. The current flowing may be in the direction shown as I1, and we will have the same current I1 in the second circuit. For example, if we do not connect anything to the two circuits, then I1 will be 0 for both circuits, and we will have a voltage V1 across nodes A and B for both circuits. If we connect anything else, for example a resistor between terminals A and B of value R, we connect the same resistor across terminals A and B of circuit 2 as well, then once again the voltages V1 and the currents I1 will be equal. In fact, no matter what we connect between the terminals A and B, the voltages V1 and I1 will be the same for both circuits. If the voltage V1 and I1 is equal, no matter what we connect to the two circuits, we say that circuit 1 is equivalent to circuit 2, and this equivalence is shown by drawing the equivalence symbol between the two circuits, which indicates that the two circuits are not equal, but they are equivalent at the pair of terminals A and B. We will also note some properties of these circuits. The first property is that only the behavior at the pair of terminals is identical. The two circuits may have different voltages, currents, and power dissipation inside them. The second property is that an element is either completely inside the box or outside the box, as shown above for both circuits. For example, we cannot have a resistor connected from inside of circuit 1 and then connected to the outside of that box. This is because if we have this resistor R2 coming from within circuit 1 to the outside, then we really have three nodes that are coming out of the circuit, for example A, B, and C. And the equivalence that we are studying in this course is at a pair of terminals only. Therefore, we will not allow for such connections when we are considering the equivalence of two circuits. Another common situation that we have to be careful of is control sources. So for example, we cannot have the control source to be partially inside the circuit. For example, if we have a voltage Vx inside circuit 2, we cannot have a controlled current source which depends on this voltage and is outside the circuit. This voltage controlled current source is considered to be partially inside the circuit too. Therefore, we will not allow such elements or element connections either. To summarize the definition of equivalent circuits, the two circuits are enclosed inside a box, and we have only two terminals coming out of these two boxes at which the circuits are equivalent. Although you may not realize it, we have already looked at equivalent circuits before. For example, if you have two resistors in series of value R1 and R2, then this is equivalent to a single resistor Req of value equal to R1 plus R2. Note that we have two terminals A and B at which these circuits are equivalent, and if we replace one circuit by the other, then we will not be able to tell the difference between the behavior at the terminals A and B between the two circuits. We will look at more complex circuits and their equivalents next. For example, consider a current source of value 3 amperes, which is connected in series with a resistor of value 10 ohms, and we have two terminals coming out, A and B, and we are interested in finding the equivalence at the terminals A and B We have drawn a dotted box to indicate what is inside the box and what is outside the box, and the two terminals coming out of the box are terminals A and B. Suppose we connect a resistor of value R to the terminals A and B, then the current flowing through this resistor in the direction shown will always be 3 amperes because of the 3 ampere current source inside the box. What this tells us is that no matter what value of the resistance R, the current will always be 3 amperes through it because of the current source. And the voltage across this resistor R will be equal to V, which will be equal to 3 times R. Note that the current through the resistor R is always 3 amperes and the voltage across it is always 3 times R, regardless of the 10 ohm resistor inside the box, indicating that this 10 ohm resistance does not matter as far as we are interested in the behavior of this circuit between the terminals A and B. Therefore, the circuit inside the box, which is a current source of 3 amperes in series with a 10 ohm resistor, is equivalent to simply a current source alone without the 10 ohm resistor. Although the voltage and current at the terminals A and B is identical between the two circuits, we may have different voltages and currents inside the two circuits, and we will enclose them in a box to indicate what is inside and what is outside the circuit. Next, we look at the equivalence of two circuits called source transformation. Source transformation can be done in the following cases when we have a voltage source in series with a resistor. For example, the circuit on the left shows this situation, or a current source in parallel with a resistor shown by the circuit on the right. Note that the circuit on the left and right have the same resistor value R. What is different between the two circuits is the circuit on the left has an independent voltage source and the circuit on the right has an independent current source. These two circuits are equivalent at the terminals A and B when they satisfy the equation E is equal to R times J, where E is the voltage source value, J is the current source value, and R is the resistance value that is the same between both circuits. Finally, note that the resistor R must have a finite non-zero value for the equivalence between the two circuits. The reason we call this source transformation is because the circuit on the left has a voltage source in series with a resistor, which has been transformed into a current source in parallel with the resistor. We will check the equivalence between these two circuits by connecting different elements between terminals A and B and making sure that the voltage that appears at this terminal and the current that flows at this terminal, V and I, is the same for both circuits. Consider both of these circuits when there's nothing connected between terminals A and B, such that the current I will be equal to 0 for both circuits. The current I also flows through the resistor in the left-hand circuit. And since this current is equal to 0, the voltage V on the left-hand circuit will be equal to the voltage source value E. For the circuit on the right, let the current through the resistor be denoted by IR. Note that if nothing is connected to the terminals A and B, then IR will be equal to J, the current source value. And the voltage V on the right-hand side circuit will be equal to R times J. And for equivalence, the voltage E on the left-hand circuit must be equal to R times J, which is exactly the condition given for equivalence, and therefore these two circuits are equivalent if nothing is connected to the terminals A and B. This was the situation when nothing was connected to terminals A and B, or they were open circuit, and the voltage and current at the terminals A and B were equal. Also note that the currents and voltages inside the box are different for the two circuits. For example, the current through the resistor R in the left-hand circuit is 0, whereas the current through the resistor R on the right-hand circuit is equal to J. Consider what happens when we connect a resistor of value RL between the terminals A and B to both circuits. We denote this situation as RL connected to terminals A and B. For the left-hand circuit, we will have I is equal to the voltage source value E divided by the total resistance seen by the voltage source, which is R plus RL. For the circuit on the right, we can identify it as a current divider where the current I will be equal to the resistor value R divided by R plus RL multiplied by J. If we substitute the condition for equivalence between circuits, E is equal to Rj, we will get that this is equal to E over R plus RL, which is the same value for the left-hand circuit. To conclude, no matter what we connect between the terminals A and B, we will get the same voltage and current at these two terminals between the two circuits, and hence their equivalent. To summarize source transformation, we are converting a voltage source in series with a resistor into an equivalent current source in parallel with the same resistor, and these two circuits will have identical behavior at the terminals A and B regardless of what is connected to the terminals A and B.